All right, today we're diving into a discovery that could totally rewrite the rules of technology. We're talking about a new class of crystals engineered to make our gadgets faster, way more efficient, and maybe, just maybe, even power themselves.
But first, let's start with a question you've probably felt yourself. Does it seem like our gadgets are kind of hitting a wall? You know, like the big, game-changing leaps in speed and power are getting smaller and smaller every year? Well, you're not just imagining it.
You see, the research we're digging into today points out that our current electronics are bumping up against some really hard physical limits. They use a ton of energy, which makes a lot of heat. We're finding it harder and harder to make them meaningfully faster. And honestly, there's only so much smaller we can shrink them.
So, to get to that next breakthrough, we can't just keep making small upgrades. We need a whole new playbook. We have to fundamentally rethink how a computer chip even works, and that's exactly what this new science is all about.
And that new playbook? It's called spintronics. Now, the name might sound like something straight out of science fiction, but it's a very real and incredibly exciting field that dives into the secret life of electrons.
So, what is it exactly? Well, for the past 100 years or so, all of our electronics have relied on just one thing about the electron: its negative charge. Spintronics basically says, hey, what if we used another property too? And that property is its quantum spin. It's like we've been building everything with just a hammer and someone just handed us a whole new toolbox.
Okay, here's a really simple way to picture this. Traditional electronics are like a basic light switch. They're binary. It's either on or it's off. That's it. Spintronics, because it also uses an electron's up or down spin, is more like a dimmer switch. You don't just have on and off. You have all these settings in between, which means we can cram way more information into the exact same amount of space.
But you know, spintronics is just a cool idea if you don't have the right materials to actually build with. You need something special that can control and read that electron spin. So, let's meet the heroes of this research paper, a family of crystals called Spinel Chalcogenides.
So this is what they look like, right down at the atomic level. And that perfectly ordered, cubic structure isn't just pretty to look at, it's like a meticulously designed cage for electrons. The very specific way these atoms of strontium, cerium, and other elements are arranged is what gives these crystals their incredible potential.
And look, this isn't just me getting excited about it. The researchers say it loud and clear right in the paper. They see these materials as leading candidates to build the next generation of not just electronics, but energy devices too.
Okay, so a material can have all these amazing properties in a computer simulation, but that's pretty useless if it just falls apart or changes its behavior at room temperature. So the multi-million-dollar question is, are these crystals actually stable enough to build something with?
And the answer, thankfully, is a big yes. What these graphs are showing us is that the crystals naturally want to be in their most stable, lowest energy state. For what we need, that's the ferromagnetic state, which just means they act like tiny magnets. In every one of these charts, that useful magnetic state is the lowest point on the curve, which confirms they are absolutely stable enough for real-world use.
Okay, so we've got stable materials, check. Now let's get to the really good part. What are these so-called superpowers that make these crystals so special? It really all comes down to two incredible properties.
All right, the first superpower has this really complex-sounding name, half-metallic ferromagnetism. I know, it's a mouthful, but the idea behind it is actually pretty simple. The material basically acts like a bouncer at a club, treating electrons differently depending on their spin. Let's zoom in on one of these materials, the selenium one. For electrons with a spin up, this material is like a wide-open 6-lane highway. They just flow right through with zero resistance. But for electrons with spin down, it's a closed gate, a total roadblock. They are completely blocked. What you get is a perfect spin filter, and that is the absolute cornerstone you need to build any spintronic device.
And the cool thing is, these magnetic properties are really robust. Most importantly, the material holds onto its magnetism right around room temperature. This is a huge deal because it means you wouldn't need some crazy, expensive cooling system just to make a device built with it actually work.
But wait, because that spintronic superpower? That's only half the story. These crystals have a second, equally amazing talent. They are fantastic thermoelectric materials. This means they can take waste heat, you know, like the heat coming off your laptop right now, and turn it directly into usable electricity.
So what you're looking at here is a graph of something called the figure of merit,
or Z0T for short. It's just the standard way of measuring how good a material is at this heat-to-electricity trick. Higher is better. And you don't have to be a scientist to see that the green line, that's the tellurium version, is just blowing the others away.
And that brings us to the magic number. At room temperature, the tellurium-based crystal hits a ZT value of 0.90. Now, to put that in perspective, a lot of commercial thermoelectric materials are in this ballpark. So hitting this number in a brand new material that also does all that spintronic stuff, that is exceptionally rare and super, super promising.
Okay, let's just take a step back for a second. We have a stable material that has two completely distinct superpowers. So what does this all mean? Why should you care?
Well, the payoff here could be absolutely massive. We're talking about the potential for data storage and processors that are exponentially faster and can hold way more data than anything we have today. We could see computers and phones that are radically more energy efficient, and we might even get gadgets that can power themselves just by recycling the heat they produce. It's incredible stuff.
This whole line of research is just a fantastic reminder that the next giant leap forward in technology might not come from a new piece of software, but from designing matter itself, one atom at a time. And it really makes you wonder, what other incredible powers are locked away inside materials, just waiting for us to find the right key?